Hey everyone, and welcome. Today we're tackling a fun Leetcode problem called Fruit into Baskets. It's disguised as a story about a farm, but as we'll see, it's actually a classic computer science pattern. Let's break it down together. Alright, here's the problem description. The main idea is that we're walking along a row of fruit trees. We're given a list of numbers, where each number represents a type of fruit. We want to pick as many fruits as we can, but there are a few important rules we need to follow. So let's simplify those rules. The most important constraints are that we only have 2 baskets, and each can hold only a single type of fruit. This means at any given time we can only be collecting a maximum of 2 different kinds of fruit. As soon as we hit a third type, we have to stop. Our goal is to find the longest continuous stretch of trees we can pick from that follows this rule. This is the aha moment. When you strip away the story about fruits and baskets, you're left with a very common problem. We're looking for the longest continuous part of an array, or a subarray, that contains no more than 2 unique numbers. Recognizing this pattern is the key to solving it efficiently. Let's walk through an example to see how this works. Say our fruit trees are 1, 2, 3, 2, 2. If we start at the very first tree, we pick a type 1 fruit. Our first basket is now holding type 1. Next, we see a 2. Great, our second basket can hold type 2. So far so good. But then, we see a 3. We don't have a basket for type 3, so we have to stop right there. The longest stretch we could get starting from the beginning is just 2 fruits. We can do better. Trying every single starting point seems slow. What if we start picking from the tree with fruit type 3? Okay, basket 1 has 3. Next is a 2, so basket 2 has 2. The next fruit is also a 2, which is fine, it just goes into our 2 basket. So we picked 3, 2, 2. A total of 3 fruits. That's better than 2. But is it the best? It turns out, the best run for this example is 2, 3, 2, 2, which has a length of 4. It only contains 2 types of fruit, 2 and 3. But trying every single possible start and end point would be very inefficient, especially for a long list of trees. We need a smarter way, and that's where the sliding window comes in. The best way to solve this is with a technique called a sliding window. Imagine we have a flexible window that we place over our row of trees. We'll use 2 pointers, a left and a right, to mark the edges of this window. We'll always try to expand the window by moving the right pointer forward, but if our window ever contains more than 2 types of fruit, we'll shrink it from the left until it's valid again. Okay, let's visualize this. Our left and right pointers both start at the very beginning, at index 0. Our window contains just the first fruit, which is type 1. The number of types is 1, which is valid. Our max length so far is 1. Now we expand by moving the right pointer. It now points to the 2. Our window is 1, 2. We have 2 types of fruit, 1 and 2. This is perfectly fine. The current window length is 2, so we update our max length. Let's move right one more time. We now include the 3. Our window is 1, 2, 3, and Houston, we have a problem. Our window now contains 3 different types of fruit. This is invalid. We can't just keep expanding. To fix our invalid window, we have to shrink it from the left side. We move the left pointer forward. The 1 is now outside our window. Our new window is 2, 3. The types are 2 and 3. Phew, we're back to a valid state with only 2 types. Now that our window is valid again, we can go back to expanding. We move right to the next 2. The window becomes 2, 3, 2. Still only 2 types, 2 and 3. The length is 3. That's a new max. Let's move right one last time. The window is now 2, 3, 2, 2. Still just 2 types. And the length is 4. That's our new maximum. Since we've reached the end, 4 is our final answer. Okay, here's the Python code that implements the sliding window logic we just discussed. It might look a little intimidating at first, but we'll break it down piece by piece. Don't worry, it follows our logic exactly. First, we initialize our variables. The left pointer starts at the beginning of the list, at index 0. We have a variable called max, picked to keep track of the best length we've found so far. And most importantly, we have our basket. We'll use a dictionary or hash map to store the fruits currently in our window and a count of how many of each we have. We use a for loop to move our right pointer through the entire list of fruits. For each new fruit the right pointer sees, we add it to our basket. If the fruit is already in the basket, we just increase its count by 1. If it's a new type, we add it to the basket with a count of 1. This is the heart of the algorithm. After we've added a new fruit to our window, we check if the window has become invalid. We do this by checking the number of unique keys in our basket dictionary. If the length of the basket is greater than 2, it means we have 3 or more types of fruit, and we need to start shrinking the window. The shrinking process happens inside this while loop. We get the fruit type at the left pointer's position. We then decrease its count in our basket. A crucial step is to check if that fruit's count has dropped to 0. If it has, it means that fruit type is no longer in our window, so we must remove it from the basket entirely. Finally, we slide our left pointer one step to the right. After every single iteration of the main loop, our window is guaranteed to be valid, so we calculate the size of our current valid window. The size is simply the right pointer's index minus the left pointer's index plus 1. We then compare this current size to our max picked record and update it if we found a new, longer stretch. So how efficient is this solution? It's really fast. Both the right and left pointers only move forward through the list. This means each fruit tree is visited a constant number of times, giving us a linear time complexity, or big O of n, where n is the total number of trees. For space, our basket will never hold more than 3 types of fruit before we shrink it, so it uses constant extra space, or big O of 1. So to wrap things up, fruit into baskets is a fantastic example of the sliding window pattern. The most important skill here is looking past the story to identify the underlying problem, finding the longest subarray that meets a condition. Once you see that, you can apply the two-pointer technique of expanding and shrinking a window to find the answer very efficiently. I hope this breakdown helped make the solution clear. If you found this useful, please hit the like button, subscribe for more Leetcode explanations, and feel free to ask any questions in the comments. And hey, if you're feeling extra generous, there's always the Boba Fund. Thanks for watching, keep up the great work, and I'll see you in the next one.